What I want to do today is I want to talk about Rust. That was my plan. So we're here at 126, and rather than doing another chapter from the book, I wanted to take today and talk about Rust because Rust is the future. The Linux kernel now supports Rust, although there is not any Rust modules in the kernel. As of the latest version of the kernel, it will support modules written in Rust like device drivers in the future, and Microsoft Windows is moving to putting Rust in the kernel also, although not yet. It's not yet in any kernel, but they are going to add it. Rust is a language designed to get rid of the security flaws in C, and it is very good. And it has, for several years, been the #1 most desired language of developers. They would rather write in Rust than anything else because it's much easier to write good code in Rust. However, Rust has been developing and hasn't really been ready for prime time. Now, so in order to use Rust, I originally planned to do this on a Debian virtual machine, and you can do that, but I just today found out an alternative. On Mastodon, like I'm saying, you should be there to learn interesting things. I learned this today. I had no idea this was around. You can just have free Linux machines anytime you want them in the cloud. That's this thc.org/segfault. It is bloody awesome. I don't know how they can do this without having people abuse the service, but all you do is open an SSH window, and then, let's clear, you SSH root at segfault.net, and it will spin up a container with Kali Linux, and the password is segfault. And it totally works. Now it's creating a server, and now I have Kali Linux. If you name -a shows it's a Linux thing, and if you do lsb release -a, you'll see I have Kali Linux. So we've been making your own virtual machine and cloud machines and stuff. You don't really need to. The only problem, of course, is you can't save anything. When you log off, it throws it away. But that's not really bad for a lot of what we're doing, and that's why I'm planning to demonstrate these projects tonight. It should work fine. I don't really need a virtual machine or anything, which is bloody awesome. And by the way, it is on x86-64, so that's nice. It's got the Intel platform, so it doesn't even matter that I'm running on an ARM machine. I've got an Intel Linux machine up there. So,
what version of Ubuntu is it?
Yeah, it's not Ubuntu. It's Kali, so it's Debian.
I thought it up there is Ubuntu.
Well, it says that, but it's not true. I think that's what Kali shows as. Uname -a tells you some part, LSB release tells you more. It is apparently really Kali.
Kali underneath is Ubuntu, right?
Well, I thought it was Debian, but maybe it's Ubuntu now. It's been various different things and different versions have gone by. Yeah, it used to be Debian, but they keep changing it. Maybe it is Ubuntu now. Anyway, it's Kali, whatever Kali is, and it seems to work. So let's give it a shot for these Rust things. I did the first little bit and made sure it's going to work. It looks like it's all going to work fine in that free cloud disposable machine. So you can install Rust, and I did it earlier, but I'll have to do it again because it forgets everything, of course. Let me fit there. They're on the screen. All right. So I don't think I need to do the update. I think this machine is automatically updated. I'm just going to assume that. So I install Rust, or install the curl and build essential and GDB. These are development tools, and they were already on there, I think. But I think Rust, what that?
Does it place a time limit on your use?
Does it what?
Place a time limit on your usage?
Well, I don't know. They said there are some restrictions. There might be a time limit. I haven't used it very much. We'll see if I run out. They said there were some restrictions, and you can pay for a feature without the restrictions. But as far as I can tell, the free version is fine. There may be some time limit. I don't know. So now I install Rust. All right.
All your installed new tools are gone, right, after you log out?
Installing what?
All your installed new tools are gone after you log off?
That's right. When you log off, all your tools are gone. It's a container, and it's thrown away. That's right. So you have to install stuff, and when you log off, it'll be gone. So now I make a directory, change to the directory, and edit a file. And then I put in some code. So this is going to be my hello world in Rust. So it's, oops, I missed the first letter, F. All right. So let's define a function main, just like there's a main in C. And here's print. Rust says hello. They use print line exclamation point for some reason, but this is pretty much just the same as C. So save this, and then you compile it with Rust C, Rust compile, and then you run it. hello, and it says hello. So I got Rust, and Rust is running. Of course, this is not very interesting. It just shows that I've got what I need. So now we can play some games. So we're going to make something called integer.rust this way. And here's some code. Now, here's why people love Rust. When you define a variable, you can just do it the old-fashioned way, let I equals 1, and then it will automatically be an unsigned 32-bit integer. That's the default. Or you can specify with a colon, this is an unsigned 32-bit integer. This, I think, is a signed 32-bit integer. And then you can print those out. So when you do this, now if you compile and run that one, which is Rust, in fact, if you just compile it, if you make a mistake, and there is a mistake in that program, it will tell you, unsigned values cannot be negated. Because I defined an unsigned variable and I tried to set it equal to a negative number, and you can't do that, obviously. So the cure is to edit that thing again, nanoint.rs, yes, how to get Kali from this link. All right, somebody asked how to get Kali from this link. You open a terminal, and
Open SSH or something.
yeah, and I thought, come to think of it, it's this page doesn't make it as obvious. There, right at the top, SSH. Yep, SSH root at segfault.net. That's what you do. I'll put that command in the chat. If you want to do this, do that. There you go. Good. All right. Although if you're using Windows, you don't have SSH in the command line. You'll have to use PuTTY or something. Unless you know how to use SSH in PowerShell, which I think it is there, but I don't know the command. Anyway, so the reason why it complained here is because I set an unsigned variable equal to 5, so I need to make it an integer, 32. That's a signed integer, 32. And now that can be minus 5. So now I should be able to compile that. And it doesn't complain, and it compiles, and it runs. So you can see here the data types, and this is a lot of why people love Rust.
Can you do a ls in that current directory? What kind of files are stored?
Sure. There you go. Executable and source code. Usual thing.
No output, no out files.
No. Yes, no out file. If you do a file on it, this is 64-bit ELF executable, and the other one's, of course, just going to be text. Yeah. Good. And so here you can learn about the data types. They'll tell you how you declare things. And so here's the scalar types: integer, floating point, Boolean, and characters. And your integers come in 8, 16, 32, 64, and so on. And they can be signed and unsigned. So you call it an I8 or an I16 or I32 for signed, and a U16, U8, U16, U32 for unsigned. And that's why people love Rust. This is the main defense. You define what's supposed to be in the variable, and it will tell you when you try to put the wrong thing in there, as opposed to C that will let you put numbers in that underflow and letters in that go out the end of an array and all that jazz. That's why it's safe. It doesn't let you accidentally put the wrong kind of data in the field, which is the root of most of these C vulnerabilities. That's why developers love it, because it doesn't trick you, and that's the point of this project. You get to see how cruel C is, and how Rust is not cruel by comparison. So let's add some numbers. I'll make an add app. All right, and so this is going to add a couple numbers. If I can get in there. That's the function. All right, there's main is A equals 1, A equals A plus 1, print A. And notice the format of how you print something is a little bit different, but it's not that different than C, just a little different. Okay, then you Rust C add. And then it warns me, no, an error, cannot assign twice to immutable variable A. Ah, yes, this is the point. So now it has errors. Now the trick here is A is immutable. And this is another thing to know. Something you do not have in C, there are immutable variables. Immutable variables, by default, they are immutable, read-only. So if you set fees equal to something, it cannot be changed. It's immutable. Python has these too. If you want to make it mutable, you have to specify mut here to make it mutable. So that's another thing. It's not that hard to do, but now you know what you're doing. And again, if you define things clearly, then you won't have mistakes. So if I put a mut in there, this should work. Let's try that. If I go back and nano this file, if I put a mut here, then it should no longer complain. It doesn't complain. And now I can add 1 and 1 and get 2. So if you look at the source code, see now it defines immutable a equals 1. Now a equals a plus 1 is okay. But it wasn't okay before. So that's just another situation where it's clear what you're doing in there. And now let's make a program with a C flaw, and let's see how Rust fixes it. So let's do, let me see where I am. All right, I want to be up here. All right, so now let's nano ovc.c. This is going to be a C program. And so I've defined an unsigned character, X, and then I put a number in there. This is just the kind of horrible stuff you shouldn't be doing, but this is what you do in C. A character is in fact a 1-byte integer. They're treated the same in C, so I can set it equal to 230. Now I just make a loop and add numbers to it. Add and add and add, like 1 through 10, and print it out. So let's compile that. Y, enter, all right. So let's compile it with GCC. And then run it. All right, so 231, you add, and when you add a number to 251, it wraps around and gets small again. Now, how is a developer supposed to know this? This is cruel. You're adding something up, and you add more to it, and it gets smaller. Now, we know it overflowed, but the fact is, nothing warned the developer. They don't really know how long the variable is. They're thinking about other things. This happens all the time. One of the very common flaws in C code, overrun. Integer overrun vulnerabilities. And you see, this is in fact cruel. How is the developer supposed to know where they're thinking about logic and they add to a variable that it might hit the peak? And this does not happen in Rust, as you might imagine. We're going to do this exactly the same program in Rust. So here's the code that does the same thing, and as you see, the code looks very similar. I set a mutable x unsigned 8 equal to 230. So it's an unsigned integer, and I set it to 230. And then I just, for a loop from 1 to 10, I add numbers to it and see what happens. So I run this. I compile it. Now, it'll let me compile it this time, because there's nothing so wrong with it that it can't compile. But when I run it, it adds, and when it overruns, it stops and tells me, you attempted to add with overflow. So you don't just add to it and get the wrong number and keep going, which is what C does, which is how you create a vulnerability. If you somehow add and the new number will not fit in the variable, it will stop and you'll have an error, and now the developer will fix it. But it doesn't just get to the wrong value and create a vulnerability, which is what happens in C. This is why you can sometimes, if something's only supposed to be 10 characters long, you can sometimes put in 16,000,010 and get away with it because it overflows and thinks it's a small number again. All right, so that's the overflow. And now let's do the famous buffer overflow. All right, we're doing a simple case of a buffer overflow, but let's do here in the nano strovc.c. All right, so what this does is it defines a string 1 5 characters long, and this one's 5 characters long, and they have A's and B's in them. Then it prints out the addresses where they're stored with the pointer variable type, and then the contents. And then you enter a new value for string 2 using scanf that will read any number of characters in, and then you just print them out again. So this should create the simple overflow where one variable leaks into the other variable. So let's run that one. And we'll compile it as usual. And run it. All right, so string 1 is sitting here at 93B, string 2 is at 936. So they're only about 6 or 5 characters apart. This one contains AAs, that one contains B. If I put in a new value for string C, string 2 of CCC, then this one is fine and that one is CCC. So a short value will fit in just fine and nothing bad happens. But of course, the problem is if I put in a long thing, then horrible things happen. If I change string 2 to a longer variable, then string 1 changes. So I put the data in string 2 and it changed the value of string 1. This is the kind of thing that will drive a developer mad. How are they supposed to know that's going to happen? This is why people hate programming in C and why they have so many vulnerabilities. Just like the integer overflow, this is just cruel to the developer. And Rust does not do this to you. We can do exactly the same thing in Rust. So we make the same program in Rust, and here it is. We make two mutable string values. Mutable string values that start out with 4 A's and 4 B's. We print out the address and the contents. Then I get a new value for string 1, and this looks a little more complicated, but this reads from standard in a line of arbitrary length and puts it in that variable. I reads that number of bytes, and then you look to print out the answer. So that's the Rust program to do the same thing. And I compile that, which is -G to keep symbolic symbols for debugging, which we're going to do later. And then I run it. Now it gives me a warning. It warned me that I don't need to make this one mutable because I'm never going to change it. I only change the other one. So that's not bad, but it's just warning me. There was no need to do that. Anyway, I run it. All right. And so here's string 1 and string 2. Notice this one is at 748, and this one is at 760. So they're a little bit further apart, but not very far apart, about 18 apart in hex. String 1 contains some A's, string 2 contains some B's. If I put in some C's in string 1, then it added it to string 1. Instead of erasing it, it added after the A's some C's, and then string 2 contains B's. So it didn't change string 2. And even if I put in a lot, oh yeah, I should put in C's. Thank you for telling me. Let's put in C's. Good. All right. I put in a lot of C's, and it put all those C's in string 1, and it didn't affect string 2 at all. However, and notice, by the way, here's something. String 1 was at 3A8, and it's still at 3A8. String 2 is at 3C0, and it's still at 3C0. And the difference between A8 and C0 is only 16 plus 8, only 24, and this is more than 24. So that's interesting. If this was C, this would have been enough to leak into the next string. And so let's debug it to see how that happens. I do GDB -Q str. Okay, now we debugged it. Now I can do a list. And since I included debugging information, you can do source code debugging. You do not need to do assembly code debugging. Here's our Rust source code. So line 7 is where it's about to input the new value. So I think I put a break there. Yep, break on 7. And run. All right, so now it has initialized the strings and stored them somewhere, and now I can examine how they are stored. You can look at these addresses with x/2x, that'll examine 2 hexadecimal words, and I can see string 1 address here, so I can look at string 1. Now, string 1 contains 4 A's, so if this was C, I would find 4 A's here. But that's not what I find. I don't find any 41s, I just find some numbers. Now, if I look at this string 2, which is here, x/2x, string 2, again, I see some similar numbers. And what's going on here is this indirect addressing. These are pointers to where it's stored. It's double indirect. What's stored at the location is a pointer to where it's really going. And so I can see what's there by examining at those addresses. I can do it with print S1. S1 will show me that the pointer is here, pointer. It's wrapping around a little funny, but that's the pointer. 5636 ending in A0. And you can see that's what it was here, 5636 ending in A0. So this is the pointer where the string 1 is going. And if I look there, let's say 4x at the pointer, that's where the 41, 41, 41s are. So Rust stores things with 2 pointers, 2 layers of pointers. And you can do that for the second one too. If I print S2, I'll get the pointer where it is. And if I examine memory in that location, I'll find the B's, 42, 42, 42, 42. So now if I continue and put in some C's, no, don't start from the beginning. Continue is what I wanted. There. Okay, now I put in some C's. Okay, and now it exited normally, so I wasn't able to examine it. I don't think I can do it. So I don't think I can print S1 anymore. No, I think I'm going to need to put in a breakpoint. So let me do it on a list. What I want to do is examine it after this input. So I guess I'll put a break at 11. Should do it. All right. So now we'll run. And here's the first breakpoint, enter new value. And so I'm going to continue. Now I'm going to put in the C's. Okay. A lot of C's. Okay, and now I'm going to print S1. And there's S1. Here's the pointer. If I examine the data there, that just contains the A's and nothing. And here's the C's, because this is where I added a whole bunch of C's. But if I print S2, that's here. And that has the B's, which are not molested. And notice, before, when I did it up here, the one pointer was at BA0, and the other pointer was at BC0. So they were only 32 apart. But now, after I reach the second part, this one is still BC0, but that one has moved to BF0. So it just moves, as it should. If you put too much data in for it to fit where it was, it relocates it to another location and changes the pointer, and goes on. So it will do what any sensible language would. It will reallocate memory as needed to whatever you put in there and move it wherever it has to move it to where there's enough room. So under no circumstances will what you put in one variable leak into another variable, which is in fact insane. Another thing will drive a developer nuts. You change one variable and it changes another variable. Why would it do that to you? And that's the buffer overflow that we missed.
Can you do a AX, the first x slash 4x, can you do the same thing to AX?
Same thing to what?
The first, when you do the x slash 4x,
yeah,
and, can you do that, change it to AX, change it to longer?
Oh, yeah, you see all of it, yes, for the first one, sure. We can see the whole long thing. 8x for the first one, which is the one of it, sure. Yeah, if you want to see it all, yep, like that. In fact, it looks like it's even longer than that. Let's try 16. Yep, looks like I put in a whole lot of C's. Yep, now I finally got to the end of them. So you have it as many as you want, and it will just find a place where there's enough room and put it there.
What was the end for that memory location to like stop reading?
Well, that's a good question. It looks like it stored the 0A for a carriage return, is what it did.
Oh, I see.
So that's a good. I do not know if it uses null for the terminators of strings in Rust. That's a good question, and I don't know. Might be that the null is the terminator, like C. Good. It's probably in that tutorial, but I don't know. All right, so that's this stuff. You see a buffer overflow, and you can, of course, have higher level flaws. So here's command injection. Let's get out of here. A nano cmdi.c. So here's command injection. All right, and let's go back and look at that. All right, so what it does is it defines an IP address of 30 characters long and then a command of 40 characters long. It prints the IP, then it does read something into the IP variable, and then it's going to string copy ping minus C1 into command and then combine them. So the idea is this is going to do a ping to that IP address. If you give it an IP address, it will add it to ping minus C1 and then execute it with a system command. This is how you typically create command injection problems. You have to execute an operating system command on a variable that includes user data. So this is the C version of the simple ping form that we exploited in a lot of versions. So if I GCC it, minus O, what is it, CMDI. All right, and I've got, I think I have just warnings. What's all this? Yeah, warning, warning, warning. Yeah, a lot of warnings, but nothing to stop me, so I can run it. All right, now I run it. Now let's see. Control C, let's try LS. Did I get one? I didn't. All right, maybe something's actually bad. Include standard IO.
You use a .c.
Oh, did I do something wrong? Let's see. All right, what did I do?
.c.
Oh, I got a, no, a bad character right there, that's why. That's why. Okay. That's what it was whining about. There. Ha! That's all it was. I had a bad character at the start. CMDI. All right. So I can give it an IP of 8.8.8.8, and it will ping 8.8.8.8. But I can give it an IP of 8.8.8.8 ls, and it will do the ping and then do the ls. So I have command injection, the typical kind. Because it combines data from the user into an operating system command. And that is something Rust cannot fix. As you'll see, the same thing happens in Rust. You have to use something called cargo to do that. You create a new Rust passage called CMDI and edit its manifest. This is all from that tutorial. And so add this line at the bottom. Command library. This is how you get this, the ability to execute commands. So down in dependencies, I have to use a command library. And now I can edit the package's source code, something you have to do, I got from that. And now it creates a hello world, but just replace it with this. All right. Put in that instead and delete all that other stuff. All right, and so this is going to do the same thing. I have a mutable string, I enter the IP, then it's going to combine those two together, running the command including this and then the IP address. Just doing the same thing. It's going to print it here, that'll create this string, and then it'll run it as a command. Just very much like C. And so it's cargo run. All right. I don't remember why I had to do this with cargo. I just followed that tutorial I've linked to a couple times that tells you how to do things. I found in there how to do this. Oh my, look at that. It's working pretty hard. It will compile and then have warnings and then run. So let's see. Now, I've run slow. I kind of wonder if they're punishing me for using this free service. Well, the other free service we used in another class, I used an online Python sandbox, and the free service there, it only gives you so much CPU and then it slows down. It's punishing you for being free, and I wonder if that's what's happened here, because that's running pretty slow. However, it's getting there. And you can't beat the convenience. You could be doing this on an iPhone. Well, I don't think I'll wait for that one anyway. The point is, you still have command injection in Rust, because Rust cannot fix this. I did deliberately take a string and execute it as a system command, so this is a logic flaw. It's not an implementation flaw. Rust has no reason to believe that I did not want to execute those two commands. This is not, there's no way it would know that. I deliberately made a string and I deliberately executed it, so this command injection is going to still be preserved in Rust. All right.
Could it be the cargo module's problem?
Yeah, it could be the cargo module is big or something. Yeah, but it's having to fetch something from somewhere, and it's getting it. It's just running slow.
No, I mean the cargo module when you look at commands, it should break out. To reject the command injection.
Well, yeah, but the point is, it can't reject the command injection for the same reason SQL injection is not a bug. I made a command and I executed it, and it executed correctly. For all they know, I wanted to execute 2 commands with a semicolon. That's a perfectly valid command.
But the cargo module should be able to tell whether there's a command coming in, right?
Yes, but it got a command, and the command was ping semicolon ls, which is a perfectly valid command. That's what I mean. The same thing's true of SQL injection, right? In SQL injection, you execute a select star from database where name equals Fred, then you put an apostrophe, name equals Fred or 1 equals 1. That's also a valid command. It has no way to know that that's a hacker. That could be the legitimate SQL command. That's why these automated defenses cannot save you in that case. You're creating a perfectly valid command and executing it. Then you don't want it, there's no way it can tell you didn't mean that. Whereas having something go out of the bounds of a buffer and leak into the next buffer, that's a flaw in the system that they can fix. And that's the thing. That's why it's nice that you tell it, I want this to be an 8-bit integer, I want it to be immutable, I want that one immutable. You tell it what the rules are, and then it enforces those rules. So it's better for the programmer because you define what you're doing, and then it acts as you expect, instead of not defining it clearly and having it do weird things you didn't expect. So anyway, that's a good point, and I think that'll eventually catch up, but it doesn't really matter. All right, and I think I'll just talk about the next one, which is more of the same. This is really the most fun, the buffer overflow, but there's more. In the next one, you have dangling pointers and memory leaks, more things. You can do a heap overflow in C, and you can do a heap overflow in Rust. And it prints out the correct value of the names. So again, you'll see it does not have an overflow. Just like the stack overflow, if you overflow the size of an object on the heap, it just automatically allocates a different size on the heap. And by the way, one thing that's awesome about Rust, in C, you have to allocate space here with malloc, and then you'll have to free it later. Although when I leave the program, it automatically frees, I think. But in Rust, you don't allocate and free. In Rust, you allocate something, and as soon as it goes out of scope, it's automatically freed. There is no free command. So you cannot have a double free, and you cannot have a dangling pointer where you forgot to free something. The free is just automatically done when it falls out of scope, which is much more clever. So it avoids dangling pointers, and it avoids heap overflows. And you can look in GDB, as we did before, and see how it works. And there's a dangling pointer where you allocate something, and then you're able to use it later. But that can't happen in Rust, as I recall. And I think there's something else here, using free correctly. Anyway, so there's more stuff to do in the next one. I don't think I'll go through it in detail. If you like the first one, you can do the second one to see more details. Oh, it looks like it finished. Good. It's finished. Now it's building. All right. Now it warns you, but this warning doesn't look like it's anything too important. It killed something. Oh. Note, warning, it says killed. I wonder if it didn't create the file to run. Cargo run. Finish dev running. And now it runs. Okay, now I can put in an IP of 8.8.8.8, and it works. And I can do run, and now I can put in 8.8.8.8 semicolon ls, and it does the ls. So, like I say, this is not something they can fix in the language. This is a logic flaw, and it does do the same thing. All right.
There's no Rust version for your RAM or for your ARMs?
For what?
For your ARM computer?
I don't know. There probably is Rust for my ARM. I didn't even try. Yep. In fact, I think there is because I successfully compiled it on my Debian on ARM. So I guess there is. The same commands just worked. That's why I planned to demonstrate it in my Debian machine, and it worked fine. I just be reading the news right before I came here, and I found out about these free cloud machines, so I thought I'd try that, and that works too. And you can't beat the convenience. So I'm going to stop this recording.